Hello everyone, my name is Ali Ehsan and I am a postdoc researcher at the University of Manchester. Today I will present my work on uncertainty propagation through integrated gas and electricity networks using a sequential Monte Carlo approach. This presentation will start with the introduction of the problem and the motivation behind it. This will be followed by a detailed description of the methodology, a case study with the description of the results, and finally the main conclusions will be presented. So the motivation behind this work comes from the rapidly increasing energy demand and greenhouse gas emissions, which bring about several changes for electricity networks such as supply security, environmental sustainability, and economic feasibility. This is sometimes referred to as the so-called energy trilemma. Additional challenges include the uncertainties arising from intermittent renewable generators, as well as the fluctuations in electricity and gas demand. Conventionally, the electricity and gas networks have been planned and operated independent of each other. But multi-vector energy networks, such as the integrated gas and electricity networks, exploit a whole systems approach with increased cross-vector coupling. In this way, these networks offer several benefits, such as secure and reliable supply, better renewable utilization, as well as reduced emissions and operation costs. Therefore, this work aims to investigate the interactions between electricity and gas networks, as well as quantify how various input uncertainties propagate from one network to the other within these networks. For this purpose, the uncertainties pertaining to photovoltaic and wind generation, as well as electricity and heat demand, are modeled. Time series profiles with a horizon of 1 week and a resolution of 5 minutes of each uncertain input parameter are determined through probabilistic models trained based on historical datasets. For the photovoltaic generation and wind generation, a first-order Markov chain-based method is utilized, whereas the fluctuations in electricity and heat demand are modeled through Gaussian distributions with corresponding parameters based on historical demand data. Once the time series profiles are generated, a sequential Monte Carlo-based integrated gas and power flow is performed, the outcomes of which are analyzed to quantify the propagation of uncertainty from one network to the other network. Here is a schematic of the integrated gas and electricity network. The electricity network is supplied through a combination of wind turbines, substation, photovoltaic arrays, and electricity storage. The electricity and gas network are coupled through a power-to-gas unit which feeds into the gas storage, which then feeds into the gas network. Please note that the electricity is purchased from the external market through the substation, while the purchased gas refers to the gas imported via the power-to-gas technology from substation. Here, the power flow model is depicted. The input specifications includes the different parameters for the gas network, electricity network, and the power-to-gas unit. The gas and power flow analysis consists of various nodal and branch flow balance equations. A Newton-Raphson based solution method is then employed. The outputs consist of the nodal pressures and gas flow for the gas network, whereas the outputs for the electricity networks include bus voltages, branch power flows, and the power of the slack bus. Now I will discuss the modeling of Monte Carlo uncertainty parameters, the first of which is wind generation. First of all, based on the historical data, the Markov chain can be employed to determine the probability distribution of transition from each wind speed to each other possible state in the form of a transition probability matrix. A partial representation of the transition probability matrix is shown here. Then, given a particular wind speed, the transition probability matrix can be used in conjunction with a random number to determine the wind speed at the next step. After determining the wind speed time series, the wind generation time series can be determined using the speed to power conversion function shown here. The second input parameter to be modeled is the photovoltaic generation, for which we need to model the outdoor incident irradiance, which is a product of the historical clear sky surface irradiance and the clearness index. The historical clear sky surface irradiance at a given longitude and latitude can be approximated through the calculation of solar position given the day of the year and the time of the day. The clearness index is defined to consider the irradiance attenuation caused by the clouds as compared to the clear sky conditions. For example, an index of 1 indicates a clear sky, whereas a clearness index of 0.5 shows a cloudy sky. A partial representation of the transition probability matrix for the clearness index based on historical irradiance data is shown here. Once the irradiance time series is determined, the PV generation time series can be obtained using the irradiance to power conversion function shown here. Lastly, the time series profiles of electricity and heat demand are based on weekly historical data sets. The fluctuations in the time series of electricity and heat demand can be modeled via Gaussian distributions, considering historical values as mean and 5% of historical values as standard deviation. The test system consists of a 7-bus electricity network, which is coupled to a 7-node gas system through a power-to-gas unit. The electricity network consists of 2 wind turbines and 2 photovoltaic array systems. For this work, 4 cases are considered with increasing renewable penetrations to observe the impact of increasing renewable penetration on the interaction between the 2 networks. A stopping rule is employed to limit the number of Monte Carlo simulations, and the rule determines the error of sample mean compared to the normal distribution mean. Simulation results show that the sample mean error converges to less than 5% for both electricity and gas purchased as the number of simulations approach 100. Hence, the number of simulation is limited to 100 for this case study. The probabilistic time series profiles for one representative week in case 1 are shown here. The goodness of fit of the proposed time series profiles is determined using the 2-sample KS test, which determines how well the distribution of a proposed time series fits the distribution of historical dataset as an entire shape. So the test results for the case 1 show the distribution of the purchased electricity over 100 weeks fluctuates between 5 and 8.5 megawatt hours, with a standard deviation of 0.66 megawatt hour. whereas the gas purchased over 100 weeks remains quite stable with a standard deviation of only 0.014 megawatt-hour. Now I compare the distribution of electricity and gas purchased over 100 weeks for case 1, 2, 3, and 4. So here we can see that for case 1 and case 2, the electricity purchased fluctuates substantially with an interquartile range of 0.855 for case 1 and 0.798 for case 2. Please note that the interquartile range estimates the spread of a dataset by taking the difference between its 75th and 25th percentiles. On the contrary, the gas purchased in case 1 and 2 remains quite stable, whereas in case 3, the gas purchased fluctuates substantially with an interquartile range of 1.337, and this further increases to 1.545 in case 4. The main conclusions of this work are that until the renewable penetration remains below 100%, high impact of input uncertainties in electricity network are observed, whereas an insignificant impact of the input uncertainties is observed in the gas network. When the renewable penetration exceeds levels much higher than 100%, the impact of input uncertainty is more visible in the gas network, which means propagation of the uncertainties in electricity network to the gas network. It should, however, be noted that the renewable penetration level at which the propagation of uncertainty from one network to the other becomes noticeable is reliant on the level of coupling and available storage capacities in the integrated network. Further research will look at the extension of proposed technique for application in larger and more complex realistic integrated networks. Secondly, we will look into the investigation of uncertainty propagation pertaining to other network variables such as energy storage, bus voltages, branch currents, and nodal pressures. Thank you for your attention.